I did a talk last year describing a bit of the technology needed to connect devices. And so this year I plan to show a bit more of how you do it and what kind of components you need to do it. So I'll go through these small points and describe a bit more about different APIs we have, and can start to tell you who we are. So we formed the FOI Labs more than a year ago, 1.5 years ago, and the idea was to build a device management system that is flexible enough to be used for various kind of applications on the embedded side. So the company's idea is, of course, to make money on the server side. But at the same time, we wanted to push Erlang on embedded and Erlang in general, because we think it's a great way of writing embedded code. So both when it comes to firmware upgrades, various fault tolerance aspects of things, it's a very simple way of writing robust code on the nodes and the device side. And we also have a background, several of us, in that field of computing in different various ways. And so both on the mobile side to connect stuff over the internet, and also to run on the embedded hardware. And that's also a bit the reason why we do it. Why are we doing this? Why are we promoting Erlang on the embedded side? And that's of course because we have been in those projects. We have been writing code on embedded systems, and we would like to see more Erlang running on those devices, because it makes lives a lot simpler, and also it makes it easier for the developer to write code that could, instead of taking weeks or months to develop, take days or hours. So that's our goal, to make it easy for people to develop applications or services using Erlang. But of course, we are slightly pragmatic now in the beginning, so we will accept any kind of protocol to connect to our device management system. So you're welcome to connect all the crazy stuff you have. So we call it Exo-device. So the whole thing is called Exosense, and Exo-server is the device management server. And Exo-device is basically for us just a collection of applications, OTP applications. And we use Rebar to compile them and collect them with GitHub. So it's very easy to just do a wrapper application or wrapper Rebar config, and then you will get all the modules you need and compile them together in something we could call Exo-device, for example. And one of those components could be Exoport, that in itself contains more applications like BERT RPCs and ExoSockets and stuff like that. So socket wrappers we've written for the software to be easy to use. So the Exo-device is just a collection of various APIs you need to write your application, and you can run it on the target or on the host. It's not a really big difference between the target and the host, and we saw that in the last speech. Now we have Erlang running on a tiny, whiny little machine, and all of a sudden it doesn't really matter if you run a TCP socket on the host or on the actual target. So we have some projects going on with Yocto. That's a kind of Linux distribution for automotive and founded by Linux Foundation. So we are involved in that a bit. And in that project we used, for example, TravelPing's Tetra Pak to build the packages. And so the hardware we use, we can use basically anything that can run Erlang and Linux would do. And now we know even one more from the last speech. So I think that's really, really cool stuff that we will integrate ExoDevice with. And so for example, you can use Raspberry Pi. That's an example. We use SBCs. There's another card we use for that we selected for some of the customer projects. But Raspberry Pi is one simple chip. You can, they throw it at you, so it's easy to find. And then you can buy an I/O card, for example, that is a bit more costly actually than Raspberry Pi. So that's a bit strange. But anyway, it's, I guess, a bit lower volume. So, but with those two cards, you can build interesting applications, different I/O applications. With the Pi face, you have some I/O, and then you have also some relays that you can wire 220 volts applications, for example. So it's a very convenient way of putting together a proof of concept hardware with Erlang, for example. But until now, it's Linux. I assume Linux as a operating system beneath Erlang, but it looks like we have something interesting going on here. So anyway, for the hardware, we have I've been developing a lot of stuff recently to support the hardware, and these drivers that I've developed are specifically targeted toward Linux right now. But I guess it's pretty easy to use. Those are APIs on any kind of library or whatever you call it for accessing the real hardware, go straight to the registers. So one example is a GPIO driver that we developed. It's a Linux using sysclass GPIO Linux. You basically use files for it, but we have written an IO version of it as well, that go a register version. So you memory map the IO registers and you go straight to it. But then you can't use interrupts, so I will come back to that. So UART is, well, Svi said that you were using SL, but that's deprecated, so you need to switch to UART now. And UART got support for, well, both serial lines, but also all the modem signaling, and you can do like flash programming and stuff like that. That needs most of the time needs this kind of signaling to put the device into flash mode. So we also wrote a very nice, or Malot here, and me wrote a very nice Flash web server that you should check out if you're interested in flashing hardware. And we also have the SPI driver, slightly different, I guess, from the one you got from last speech, and I2C. And then I also wrote recently an Ethernet driver that can be used for filtering packets or access any kind of packet using BPF with a special compiler. And it makes it possible, for example, to switch packets to on the Erlang process level. So it's a several layer of Berkeley packet filter, combining it even down to the network card if the kernel supports it. And then last year I presented the CAN driver. It's still there. And I also tossed in here the PyFace interface, and this combination of the GPIO and the SPI interface. So, and there are some more, but I will stop there. And all of them, you see the addresses there. If you write GitHub in front of them, you will find the actual open source implementations, and currently at Linux. Except for UART, actually. It runs even on Windows nowadays. And so here's an example how you can use GPIO and with interrupt. So I've seen a lot of implementations that can do clear and set bits, but we focused a bit on to do what I think is very essential. So I would say that interrupt handling is as important for low-level programming as message passing is for Erlang, and here I combined the two. So I can set an interrupt for a certain condition, and it maps into the Linux, and then I can get a message when that interrupts occur. And this example ties very well into how you interface the SPI interface towards the pi-phase card, because this is what you get when someone push a button, for example, on the pi-phase interface card, or when you get the digital input. So then you need to go and read the value from the SPI interface. So it's a working, very tiny, whiny little example. So it's not more complicated than that. And so on the, what I would say, system API level, I also have added some convenient, nice to have interfaces toward the AF Unix, the local socket interface. So it's kind of named pipes, and it connects also to Gen TCP, if you like. So it's registered, and you can use the same APIs as that. It's used for the dbus application, really, or the dbus service. So I will come back to that. fnotify is a way of getting file system events for changes on disk files, and it works on Mac, Linux, and Windows right now. So you can get asynchronous messages from file activity. So it's quite nice, actually. So KVDB is also one of those system APIs that we can map key value storage towards level DB or ETS or SQLite or whatever it's needed on the device. So in this case, we have built KVDB to be able to do any kind of key value database on large scale on level DB, or on the device side we use ETS, logging ETS, or we use SQLite, where it's very convenient with a single file for the whole thing. And I also push for non-existing stuff, and that's, I think Bjarne will have a question for me later on about when it comes. So it's EPX, it's a pixel library. It's been around for quite many years now, but it's never been released. So it was designed as an Erlang pixel library. So it connects very tied to Erlang. It was designed to be used, but we used it actually in C and C++ code. But now it's back again on Erlang, so I will open it up very soon, as soon as I got some more documentation. And then I have something we call services on the service level. So last year we showed CAN Open, and then I've added Netlink, dbus, GSMS, that's SMS services for GSM modems. And I'm working on the GSMux. It's quite complicated for various reasons, but it kind of works. So it's a multiplexer for the GSM modem standard. So you can use several virtual terminals. So you can send SMS and run GPRS at the same time as you read GPS positions, for example. Some of those modules you have GPS as well. And GPS is the next topic. It's NME 0183, and it's the standard for reading GPS over serial line. And I also have BERT listed here. So those services I tend to structure in a very similar way to make it very simple to use. And so here's the structure for the GSMS, an SMS router. And if you read it from top to bottom, we can see that on the top we have the applications, and they want to receive an SMS. So they put in a subscription, a filter, that can filter out some SMS coming along. And the filter condition could be anything from a regular expression match on the body to what kind of alphabet they're using, or what kind of port, if it's an 8-bit application, and so on. And they hook up to the GSM router. And from the other side, you have the provider interfaces, and they consists of different kind of GSM 710 implementations for various modems. And going further down, you have the UWort application, and below that you have different kind of kernel modules that will support that. So it's this structure makes it very simple to route SMSs up to applications based on conditions that they need. So you can share the same modem, the GSM modem, for various purposes. Well, they can collide, but then it will pass copy to if two subscribe on the same condition, they will get one copy each. So here's an example how it could look with a GSM service. You start a small service with a subscription on a regular expression filter, and it looks like it's looks for numbers. If you look at the filter definition, it's like a regular expression. Yeah, and you can have a question mark afterwards. So question mark plus minus. Yeah, question mark plus minus. You can end with question mark plus minus. So you create the subscription and you loop with the reference from the subscription. And when you get an SMS, you process the command, and then you loop. And what can we do? Well, we can, since we know the structure, we parse the message and see if it's a pin number, plus, minus, or question mark. And then we do, the different cases. We set the pin, we clear a pin, or we ask for the value of pin and return it to the sender. So this is a very simple SMS service in a few number of lines, complete. So this you can run and get a nice SMS service, interfacing the pi phase, for example. So, and this is an example. You see the basic structure is the same. I just showing the to get the idea. And this was something I showed last year also, the CAN router. So you see how the GSM router is modeled. Makes life very simple to be able to do all these providers from below and also have a dispatching interface on the top. And of course we did something similar, but not really on the packet filter, on the Ethernet drivers. So the set filter is set Berkeley packet filter. It's a compiled Berkeley packet filter. And the syntax I can support is, you can see over there, it's slightly different than, you can hand in BPF programs if you like, but this syntax you can see over there is slightly easier to use, I would say, because it's just a simple expression. Capture most of the stuff you want to do. And as I said, you push the filters down to the driver, to the Erlang driver, and the Erlang driver will combine the filters down to the kernel. So it will put them together so that you get the kernel filter with you will join them before you do the subscription or the set filter operation down to the kernel. And the process to the right, up to the right, the ETH process, it's actually the process that do this work. It collects the filters and combine them and push them down to the kernel. And the kernel can also push down to network interfaces that to support them. So that's what bits and pieces of different various libraries. And yet some words from last year on Exosense. So from the server side, we use a very simple store and forward RPC engine. It's using BERT or Erlang messages to send to the device, and the device basically unpack that BERT message, execute, return a BERT message back. Simple as that. So from the client to the ExoDM server or Exosense server, whatever you call it, you use JSON RPC. So hiding the binary part from the customers, but making it very easy to parse and handle on the device side. And we also use Yang data models to specify what kind of messages are allowed and get some structure on those messages and control. So now we have SMSs, we have some like cool libraries. We need a way of connecting the device. So typically a device is, maybe it doesn't got any kind of network connection. Maybe it only got a GPRS modem. So we need that device to, well, it could be connected all the time, but that's not very probable. So you need a way to signal to it to say connect to the network. And well, hopefully it connects to the ExoDM servers because that's us making money. So what we do, we have just sketched a very simple protocol. And so it's a text using the default alphabet. It's a regular SMS. It's preferably in one segment, so it doesn't require multiple segments to send. So the ExoDM server will send this text message and saying ExoDM RPC, and then the required reply mechanism if you want to reply through SMS, or nothing at all, or GPRS, or in some preferred order. And then you have a base 64 encode Erlang binary message. That's a BERT RPC call. And looks something like this. So this SMS trigger is also, since we have this SMS structure where you can subscribe to various regular expressions, it's very simple to make this kind of expression that's subscribe on exactly this message. So you have one small application that subscribes to this trigger message, and that application can then run, start a PPP daemon, check the netlink status to see if we got an address, see when we get the correct flags and the interfaces up, and then we kick the applications to connect and start processing the queue and receive messages from the server, or sending messages towards the server, or receiving commands from the server. So, and you can also see, you have the same problem, regardless if you have a network or not. I mean, it could be a device behind a firewall that is just not waking up, or not understanding that it should connect or something, or it's by purpose you don't stay connected. So you could still have a good reason for sending a trigger SMS to that device so it connects through the firewall and stay connected. Or maybe you want to do something else. Maybe you want to query some device that do not show up. You can see if you can reach it through an SMS, but since you can get a reply through SMS if it's not too long. And the providers do support receiving SMS as well. So the trigger part here, I mean, we have integrated with one push SMS service, for example, and they were cheap and they only support exactly that one message. That's only text. So if we can handle that very simple cheap services, then we also have a good way of telling our customers that you can use this service and it will cost you nothing to ping your devices, or very little anyway. So last year built an application for showing off communication between a mobile app and controlling a CAN bus, and also RFnet. Is that the correct picture? No, it's not. All right, okay, I see. It was animated since last year. So this is a proof of concept demonstrating the different APIs we got. So we have the Pi face and the Raspberry Pi down there, and we have some of the old stuff with the RF that we can send signals, receive signals. Since we switched from the Telstick to the Telstick Duo, we can receive RF signals. So we can have remote control, receiving remote control signals. And we can send RF to control the plugs, the wall plugs for the different light bulbs. And we also have this interface that's, since we have these relays over here, we can have 220 connected also and switch that off. It could be anything that you have in 220, a fan or a pump or whatever. And you have both, on the Pi face, you have both input and output, so you can really do interesting stuff here. And also some control from the ExoDM, so you can send from a web page, go in and send them and activate those lamps as well as locally sending it. And another new thing is that you can send an SMS to control it as well. There is also ways of getting SMSs on events. So for example, if someone push a button, you can get an SMS back saying, okay, someone pushed the button. But that cost money, so I disabled it for the demo that's outdoors. So if you want to see it live, it's outdoors, behind the wall towards the big conference room. So, and I think it works most of the time. So, and the idea, I just heard Joe speaking about Plex, and I realized I reinvented Plex. So because I think it's kind of interesting that you have these kind of inputs, different events. It could be a GPIO or interrupt that you saw earlier, or it could be an SMS or CAN message, or an RF message, since we use the Duo now, that you can receive. And it does pretty nice, the Duo do pretty nice decoding as well, so you have a range of different things to match on. So, and then you go to the RF zone rule matcher, and you will produce an output. It could be any one of those, and including email in the output, or Exosense RPC outputs. So, I mean, it's not the application. This is just a proof of concept application. You can play around with it. I think I forgot to put it on the reference to it, but if you saw the speech last year, you will find it anyway. So it's also something you can have a look at. It's open source. So the input processing looks pretty much like if you do a table, you have on the left side the events that you want to match on. On the right, you have the CAN messages you produce. So what ends up in the center of this little switch, if you think about it this way, it's the CAN messages. And on the output side, it will match CAN messages and produce, well, emails, SMSs, or new, GPIO or whatever. So you reduce all events to signals, and then you get signals that could reduce to other signals or to outputs of different kinds. So it's pretty simple stuff. And just some final words on GSM and GPRS modems. So I had hoped to be able to demonstrate a new GPRS modem, but for various reasons we couldn't finalize it, so I didn't bring it. But it's so since ages, I mean, everyone that's been playing around with PPP or GSM modems, or modems for that matter, they know how hard it is to get all the PPP settings correct and working, and it's not very portable, and you go from one operator to another, and it's completely different, and it's totally whacked. So we wanted some way to at least get rid of some of those problems, so we thought maybe we could just build a modem for the Raspberry Pi that we could, for example, put in between the Raspberry Pi and the I/O card. That way we would have a very nice little packet of cards working together, and it would be, very easy to have software ready to roll for it. So know your modem and don't switch when you got the settings right. So that's the idea. But also we would like to add some features. We would like to add cool features. We would like to add that we can listen to the ring signals from the modem, so we can use it for power on Raspberry Pi from the modem, because Raspberry Pi they don't support sleep mode. So, but by halting it and have a small circuit on the modem, we could use the ring signals or any kind of timer logic to actually activate the Raspberry Pi by power cycling it again, and saving some, precious power that normally keeps the engineer happy if they can save some watts here and there. They will build it for you if you can argue for that. So, and also that we need all the pins that has anything to do with resets, power cycling, or the power key for those modems. Yes, so I hope I can demonstrate that in a later time. I can bring that modem. It will be something ultra cool and ultra power saving. And so when you have this modem and you have control over everything, and you know exactly how the modem signals work and how PPP connects to the modems, and if you use flow control or what kind of flow control you use, well, then you would like to maybe set up a GPRS connection. But if you want to receive an SMS at the same time as you have a GPRS connection running, could happen. I mean, then there is a solution. Several of the vendors of modem, GPRS modem modules, they support this called CMUX mode. And it's the GSM 0710 standard. And it makes it possible to implement virtual ports. And my solution, I've tried a lot of different software for it, and it is crap, everything. It doesn't work. You can't, they don't support your modem, or they just crash and burn. So of course you write it in Erlang. So here's an attempt my attempt was to write an Erlang program that implements CMUX, and using UART PTY mode. So the UART modules also support PTY, making it possible to set, like here, symbolic links to something we could identify and also be consistent every time you start. So it will be number 1, 2, 3 on the level 0. It's nothing. It's the same thing. So over USB, it can come up with various names, and you have to find a way to make it stay. So like here, for example. So if you have UART FTDI-based cable to an external modem, you normally have this name, USB 0. There are various ways of renaming it or setting symbolic links to find it, or to go into the various strange directories where you can find mappings. But so the GSMUX program is an Erlang program that we create channels to handle the proxying between the PTYs and this UART. So the flow will go back and forth here. I still have something to do, some stuff remaining with flow control, especially hardware flow control, but then it will work. So, and then you can have one modem, and you can, send SMS, run GPRS, and then you can run this as a separate node, so it can run separately as a service. And then you have your application node separate. So because if you have this structure, you can run you want to run the PPPD on one of these, the Linux PPPD. I think Klakke never got the PPPD implemented in Erlang, but I think you made an attempt, didn't you?
Long time ago.
So anyone that have a decent PPPD implementation in Erlang? Aye. Yes, thank you. So I think I stop there.
Okay, so we have plenty of time for questions. If you have one, raise your hand. I'll bring you a microphone.
Speak.
You said you have kind of what's called content-based publish subscribe, so you can subscribe to messages according to regular expression.
Yeah.
Is the filtering happens on device or on the server side? And if it happens on server side, how do you make sure that it will scale with if you have a volume of messaging?
Not on the SMSC, so this is a local, also on the receiving host. So just making it possible to have several applications listening into several modems, for example, and dispatch exactly the message you want, or at least as close as you want, with some regular expression matching or some other criteria. When you use when you use regular device management, you have another alphabet and you have a port concept in the SMS that you don't normally see, and then you can, for example, do subscription on the port number. So that's a more natural mapping for like binary services. But in this case, we wanted to build something that didn't support binary messages, so we just used the default alphabet. So, but it's not on the server side, or it's not on the SMSC or anything like that. So this is on the target.
Are there any other questions? No?
Jonna, you were supposed to ask me something.
What graphics?
Oh, the graphics. Yeah. So I have one user in the room for EPX. And he's over there. He made the previous presentation. I don't think he'd done much with it yet, but I hope he will very soon. Yeah. So, but I think it's not far away. So we're using it in customer projects, and we are documented it slowly, and it will be something that we release soon. And I hope it will be dead simple to use. No. Basically, very little documentation needed to be able to run it.
Are there any other questions? Okay, we have a break, and we will be resuming again at 4:25 with a discussion about tailflow. All right, thank you. Thank you, Tony.
Thank you.